In this tutorial, we're going to learn how to estimate criterion-related validity using a correlation coefficient in R. So to get started, we have this data file here, which is called selection data with a capital S and a capital D and no space between selection and data, the two words there. This is a comma-separated values or .csv file, which is relatively easy to read into R. And as you can see over here to the right, we have our RStudio session here. So let's go ahead and get into it. I have already taken the liberty of saving this data file, this toy data file here, into a folder that we can subsequently set as the working directory, and I have saved it into my H drive R workshop folder, which you can see right here. So here's the file, selection data, and it is again a comma separated values or .csv file. So with that being done, we're all ready to go to get into our RStudio session here. We open up, we see the R version we're working with, which is 4.0.3. Let's go ahead and clear out the console here by going to Edit, Clear Console. And the next thing that we're going to do is we're going to go to File, New File, R Script in the dropdowns. That's File, New File, R Script. And we're going to open up an R Script editor window so we can more easily track our script or our code that we are writing and make it more reproducible, more shareable, and so forth and so on. So the first thing that I'm going to start with is just make a note here at the top using a hashtag annotation that the purpose of this tutorial is to estimate criterion-related validity using a correlation. So that is our focus here today. And so what is a correlation? Well, a correlation in this context, when we're talking about criterion-related validity, a correlation can be used to estimate criterion-related validity where the data can be gathered using a criterion-related validation study or design, however you'd like to call it. And so some examples of criterion-related validation designs include a predictive validation design where the predictor variable and the outcome variable or the criterion variable are measured at two different time points, and specifically the predictor variable is measured at a time point at some point that precedes the measurement of the criterion or the outcome variable. A concurrent validation design, on the other hand, both the predictor and the criterion or outcome variable are measured at all about the same time. Now, note that when I say the word criterion variable in this context, think of criterion as meaning an outcome. But in the context of criterion-related validity, think of criterion meaning outcome-related validity. So when we estimate a correlation, and specifically a correlation coefficient in this context, really the correlation coefficient can be referred to as what's called a validity coefficient. So a validity coefficient. So again, when used as an estimate of criterion-related validity, a correlation coefficient can be referred to as a validity coefficient. So that's important to remember here just to get some of the terminology squared away. Now, the specific criterion-related validation design that we're going to be focusing on today, for which we have data, it's going to be one in the context of employee selection. And specifically, let's imagine that the data were collected as part of a concurrent validation design where the selection tool scores, which are going to be our predictor variable scores, were collected at about the same time as the criterion variable scores, where our criterion variable is going to be a job performance variable. And so we'll assume that current job incumbents, or in other words, current people holding a particular job, were the people that participated in this concurrent validation design study as part of a selection tool validation study in this organization. So now that we have the concepts of criterion-related validity and a validity coefficient defined and clear, hopefully, let's now talk about what a correlation coefficient or a correlation means in general. So I'll make a few more notes here. So a correlation coefficient represents the sign and the magnitude of the association between two variables. And we're going to be focusing today on what's called a Pearson product moment correlation, which often we just refer to it as just a correlation. But again, the technical name of what we're doing today and estimating is going to be a Pearson product moment correlation coefficient. Now, we use a Pearson product moment correlation when both variables are continuous, which means that both variables can be described as having an interval or a ratio measurement scale. Now, notably, you can also run what's called a biserial correlation, or sometimes what's called a point biserial correlation. And that's going to be used when one of your variables is continuous, meaning one of the variables does have that interval or ratio measurement scale, but the other variable is going to be dichotomous, which means it has a nominal measurement scale with just two levels or categories. So you can usually run with most functions seamlessly run either a Pearson product moment correlation or a biserial correlation, so long as at least one of your variables is continuous and the other variable can either be continuous or dichotomous. The interpretation will be exactly the same in terms of the correlation coefficient that we generate from either a Pearson product moment correlation or a biserial correlation. So let's talk about the statistical assumptions that need to be met for a Pearson product moment correlation. So we'll talk about the following 6 different statistical assumptions that need to be met or satisfied. We're not going to get into these in detail in terms of doing diagnostic tests, with the exception of looking for that there's a linear association between the variables, evidence for that, as well as a bivariate normal distribution. But the other ones can be relatively easy to test, and I should say that with the exception of the first one, which is knowing whether or not the cases are randomly sampled from the population, meaning that there's roughly an equal chance of each person or each case or observation in the sample having been picked from the population to be in the sample. One of the best ways to do that is to use a random sampling approach. And so we'll assume for the sake of our tutorial today that the data that were collected as part of this concurrent validation study design were the employees were actually randomly sampled from a broader group of employees that represent the population of employees in that organization. Now, the second statistical assumption that needs to be met is that each variable shows what is called a univariate normal distribution, and you could check this out by making sure that you see that bell-shaped curve and that you don't note any significant amounts of positive or negative skew to the distribution, and you can run a histogram, for example, to try to detect whether or not there is a deviation from normality. The third statistical assumption is that each variable is free of univariate outliers. And so using that histogram, for example, with each one of your continuous variables if you're running a Pearson product moment correlation, with each one of those continuous variables, you can run a histogram and make sure that it doesn't have any notable skew to it, either positive or negative, or perhaps you run a box plot and look to see whether or not there are any cases or observations that fall beyond the whiskers in the plot and those outer bars that you might see in a box plot. The fourth statistical assumption that needs to be met is that the variables are free of bivariate outliers. And so bivariate refers to two variables, so variate variables. And so when we plot, for example, the two continuous variables on a scatter plot, we should not see any cases that seem to be extreme values that deviate from kind of the cluster of cases. Now, in terms of the shape of that distribution, the bivariate distribution, that's where we come to the fifth statistical assumption for a Pearson product moment correlation, which is that the variables demonstrate a bivariate normal distribution, which looks kind of like an American football or an ellipse shape. And this is actually something we're going to be testing today by looking at a scatter plot. And that brings me to the last statistical assumption that should be met for a Pearson product moment correlation, which is that the association between the two continuous variables should be linear. And so approximately we should see a linear trend if we were to plot them as part of a scatter plot, the two variables. And so we'll also be looking at this statistical assumption today by generating a scatter plot before we go on to determine whether it's appropriate to actually estimate a Pearson product moment correlation with the two variables we're going to be focusing on today. Okay, so now that we have that set up and these notes out of the way, clean up the script a little bit here, and I'm going to come down, and the next thing we're going to do is set our working directory. And our working directory is going to be whatever folder we saved our data file into, and that data file hopefully contains the data that we would like to correlate at least two variables. And the data file we're working with today, again, contains data for what we can assume to be a concurrent validation study design meant to help us do selection tool validation. All right, so to set the working directory, I'm going to use the setwd function. And within the parentheses, I will type in the quotation marks. And I happen to know off the top of my head that I have saved, as I showed you earlier, that selection data file into my H drive, our workshop folder, where I tend to save everything for these tutorials, and I can click run. And so I've set my working directory. You see blue font down here. It looks successful. Alternatively, you could go to session, set working directory, and choose directory in the drop-down menus, session, set working directory, choose directory in the drop-downs, and you could go and search for whatever folder it is that contains your data file. Note that when you are doing it this way, you're searching for a folder, so you won't be able to see which files are within the folder that you tried to open and set as your working directory. You'll just have to trust that it was the correct folder, given that you saved it there. All right, and when you find that folder, just click open. Okay, so the next step is we need to read in the data. And specifically, it's the data file and a .csv data file. So comma separated values. And to do so, we're going to use the read.csv function from lessR. And so when we're reading in the data today, let's figure out a name for what we'd like to call this data frame object that we're going to assign the data frame to once we read it in. Let's just keep it simple and call it df for data frame, and that's a lowercase d and a lowercase f. We'll use the left-handed arrow operator to now do assignment of the data frame we're about to read in and to assign it to that object that we're calling df. So the name of the function we're using is read.csv, all lowercase, and it's from lessR, so we don't need an outside or an additional installation of a package to use this function. It is read.csv, all lowercase. So within the function parentheses and then within quotation marks within those parentheses, we need to type in the exact name of the data file, which I remember was selection data with a capital S and a capital D and no space between the words and the letters there. Just be sure, because it's a .csv file, we're using the read.csv function, that we need to add the .csv extension after the exact file name. And remember, R is case and space sensitive when it comes to file names or to many different features of the language, such as functions and so forth. So it's good to begin in the habit of just making sure you get the case sensitivity and the spacing correct. All right, so let's click run there. And so now you will see that we have successfully read in the data and assigned it to an object called df. If we come over here, we see that this data frame has 163 observations or cases. In this case, each one of those observations is a unique employee, and there are 4 variables. And you can get a snapshot by clicking this down arrow here. Here are the 4 variables, but let's take a closer look here by clicking on the data frame name there. And you'll see that the 4 variables are as follows. We've got an employee ID variable here. And so the employee ID variable is just a unique identifier variable. We're not going to use it here today, but this is just to indicate to us that these are actual employees. Well, not real employees. These are simulated data, but that each one of these rows represents a unique employee here. Now, the variables that we're going to be focusing on here today are just going to be the conscientiousness and performance variables. So conscientiousness, let's imagine these are scores on a conscientiousness personality inventory that was administered as part of the selection tool validation study. And so here you can see the scores there represented. And so let's assume that this is a multi-item scale and a composite scale was already created for us, and that a 5 would indicate high levels of conscientiousness, and a 1 on this scale would represent low levels of conscientiousness. Okay, with the theory and the research suggesting that to a moderate extent, conscientiousness tends to positively correlate with job performance or task performance more specifically. Now, the next variable that we're going to be focusing on is our criterion variable. So this is our outcome variable that we're going to correlate conscientiousness scores with, and that is our performance variable. So this performance variable, let's assume that it contains job performance evaluation ratings for the current job incumbents, and potential scores in this variable could range from, let's say, 1, and that would indicate does not meet performance standards, to 5, meaning exceeds performance standards. Okay? So again, we're just going to focus on conscientiousness as our selection tool predictor variable here today, and performance as our criterion or outcome variable here today. If you want to practice running a correlation between let's say this middle variable here is the structured interview, where higher scores mean better performance on a structured interview that perhaps measures applicant experiences, knowledge, and so forth related to the job. By all means, you can do that, but we won't do it in today's tutorial. Okay, so the thing to note here is that conscientiousness, the variable is spelled with a capital C, and performance is spelled with a capital P. All right. the next thing that we are going to do is we are going to generate a ScatterPlot. And both the ScatterPlot and the correlation function we're going to be using today, and there are many other functions we could be using, or at least multiple other functions we could be using to generate either a ScatterPlot or a correlation. We're just going to use two functions from the lessR package because these functions from that package tend to come stock with a lot of diagnostics and other information in the output that saves some time. So the first thing that we are going to do is install the package, and specifically that's the lessR package if you haven't already or you haven't done so recently. And so when we install a package, we do the function which is install.packages, all lowercase, and in the parentheses we type quotation marks. Bring this parenthesis back up here, and then within those quotation marks just type the exact name of the function, making sure that you get the case sensitivity correct for that function. So it's less, all lowercase, and a capital R, all one word there. Now I have recently run this function here, and installed it, so I'm not going to do it again because this one takes a little bit of time to load, so to save time, I won't do this, but if you have never used this function before, or rather this package before, the lessR package, please go ahead and run this so you can install the package so that later you can access it. But if you have installed it recently, no need to worry. You can probably skip this step here. If you do want to skip this step, one thing you can do is just add a hashtag annotation before it, just so that if you run this script all at once again, you can save time by not reinstalling the package each time. All right, but what you will certainly need to do if you have a new RStudio session and therefore R session open is use the library function from base-R and type in the exact name of the package. You don't need to put quotation marks around the package within the function parentheses for the library function. And again, it's less, all lowercase with a capital R. And so assuming you've installed the package, you're ready to access it so you can access the functions or check those functions out of the library so that you can use them. Okay, so this one can sometimes take a little bit of time to run. It's one of the few functions this package can take a little bit of time to load and when you are using the library function, and it's one of the few packages where you will get red font when you load it, and that's not necessarily a bad thing. Simply, this is just background information. It tells you the version of the package as well as some useful information and where to learn more about it. And so you can see that right here. All right, so that means that we are now ready to make a ScatterPlot. Now you can spell ScatterPlot as one word or two words. I'll just use two words here. And the name of the function that we're going to be using from the lessR package to generate a ScatterPlot is called ScatterPlot with a capital S and a capital P. So that's all one word, capital S for scatter, capital P for plot. And so let's now focus on the arguments that we are going to use within this function to specify first which two variables do we wish to generate a ScatterPlot for. So typically it's appropriate to generate a ScatterPlot when we have two continuous variables, which is the case. We have two relatively continuous variables here because we can assume here, let's say that the conscientiousness variable here is an interval ratio or interval measurement scale. It doesn't have a meaningful zero value, or in other words, zero on this actually doesn't exist on this scale, and so therefore it doesn't mean the absence of conscientiousness. And let's also say that performance is also an interval measurement scale for the same reasons. So that would make them both continuous variables more broadly. And so let's just, out of habit, type x equals, you can think of x meaning the predictor variable, x equals conscientiousness. With a ScatterPlot, whatever you type in x, this is going to be your x-axis variable. Okay, so you'll see conscientiousness along the x-axis here. If you wanted to switch this, you could do that as well. So the second variable is going to be y equals, and this is our performance variable. Just remember, you have conscientiousness with a capital C and performance with a capital P. If you want to make sure you get the names correct, you might just come down to your console quickly, type in the names function from base-R, type in the exact name of your data frame object, and then hit return or enter. And you could just copy and paste the exact names from that data frame in to make sure you don't have any spelling mistakes. So the y equals, just this argument tells us which variable is going to be on the y-axis. Again, you could flip-flop these variables if you wanted to, but conventionally we put the predictor variable on the x-axis and the criterion or outcome variable on the y-axis. All right, the last thing that we're going to do is add another comma and therefore another argument here. And after that comma, we're going to type data equals, and then the name of our data frame object that contains both of these variables. So we know that that is df, lowercase d, lowercase f, so type that in. Okay, because I have blown up my window a bit here, I'm going to open up the plot window so I don't get an error message when I run this, but I'm just running the whole function there that we just specified. Run that selection. Okay, and so here you can see, again, as I said, because we put x equals for conscientiousness, that is our x-axis variable here, and performance is our y-axis variable. So you're rarely going to get a scatter plot that's very clean. This, believe it or not, you can probably see here, this has a positive trend to it. So you can imagine that this is a positive correlation that we're viewing here. And how do you interpret a scatter plot? Well, each one of these dots represents a unique, each case's combination of their conscientiousness score and their performance score here, okay? So you can think of it sort of like battleship coordinates if you're familiar with that old board game. All right, the other thing we're looking for here is that assumption, that statistical assumption from above, which is that they demonstrate a bivariate normal distribution. Well, you can kind of see an ellipse shape here, which is that American football shape that we're looking for that suggests a bivariate normal distribution. I also don't really see any bivariate outliers that are very notable here. The scores seem to be relatively clustered within a reasonable range of one another. And the association between these two variables visually looks like it's relatively linear. You would just, if you saw something that was a pronounced curvilinear shape or something like that, you would want to hesitate because then it would not likely be appropriate to run a Pearson product moment correlation. You might run a polynomial regression or something like that instead. Okay, so if you wanted to save this plot as is, you could just go to Expert, save as an image, save as a PDF, or you could copy it to a clipboard if you wanted to do it that way. Okay, but let's play around with this just a little bit more. That what I'm about to show you is just going to be optional. These are just some stylistic things you could do. I'll just make a note here that we'll do some optional stylistic aesthetic changes to the scatter plot that we just created. And so what we'll do is we'll just grab, copy, and paste exactly what we just typed above. And now we're just going to add some additional arguments. So for example, if we wanted to change the x-axis and the y-axis labels, we could use the xlab equals argument here. And let's say we wanted to expand this. So instead of just conscientiousness on the x-axis, which is just the variable name, within quotation marks after xlab equals, we could just type in conscientious test score. So maybe that's a little bit clearer to someone who's reading this. Add a comma outside the quotation marks. And then we could also do ylab equals for the y-axis label. And so maybe instead of performance, we want to make that a little bit more specific and just call that job performance score. And outside of the quotation marks, we can add another comma here. And then another thing that we can do is let's draw an ellipse shape or superimpose it over this to hopefully make it clearer whether or not we've met that assumption of bivariate normality. And so to do that, you can use the ellipse equals true. So ellipse equals true argument. Click run. All right, and so now you see we have an ellipse shape there. We've also updated the x-axis label, the y-axis label here. And so this gives a little bit more confirmation. Okay, this kind of visually we can start to see, yeah, most of the scores kind of fall within this bivariate normal distribution. I think we can be reasonably confident in this case that we have, or let's just assume for the sake of this tutorial, that we have met the statistical assumptions that need to be met in order to feel justified in running a Pearson product moment correlation, which is what we're about to do now. Okay, so now that we've visualized the data and checked out those assumptions of linearity and bivariate normal distribution, let's now estimate a correlation. Okay, and so to do so, we're going to use the correlation with a capital C, correlation with a capital C function from the lessR package. So it's correlation with a capital C, and we're going to let's just go ahead and copy and paste the exact arguments from the ScatterPlot function and paste them into the correlation function parentheses, because it'll take the exact same arguments there. Now, one thing I didn't show you earlier is that when you go to your console here, you'll note that when you ran your ScatterPlot, you actually get a Pearson's product moment correlation automatically. So you don't technically, if you want a correlation, need to, if you've run the ScatterPlot in the lessR package, like I said, the lessR package functions tend to pack in a lot of extra information in the output. You don't necessarily need to run this correlation because you've actually already computed a Pearson product moment correlation below. You get your sample size, which is 163 cases with paired values, so no missing data here in this case. And the sample correlation of conscientious and performance is R equals 0.469. And you get your associated p-value and your 95% confidence interval. So it's kind of a one-stop shop here. But I'm showing you the correlation coefficient or the correlation function from lessR in case you didn't want to run the visual and you just wanted the correlation. All right, so with the exact same arguments as the ScatterPlot function, let's go ahead and run this and take a look in our console. As you can see, it's essentially the exact same output that we saw for the ScatterPlot function, except we also get the sample covariance, which is S equals, but we're really interested in the sample correlation, which is our estimate of a Pearson product moment correlation here, which is R equals. So little r is the conventional notation for a Pearson product moment correlation. Now, so you want to ignore, for the most part, the sample covariance because this is not a standardized metric here, and it's not really something you can easily or at all interpret it in its current form. So we'll focus on this here. So this is our correlation coefficient. And when we are interpreting a correlation coefficient, and reporting a correlation coefficient, it's often important or a good idea to report the following. And so first, if you're reporting, typically we want to put at least in parentheses in a write-up or something like that or a presentation, R equals, because again, little r stands for correlation, equals 0.469. And then you find the associated p-value. It looks like the p-value it says equal to 0.000. It's not actually a 0 p-value. It's just a very small p-value, and there's just some rounding here. And so in that case, typically what we do is do p is less than 0.001 if you have 3 zeros like this. In other words, and we'll talk about this more in a second, this correlation coefficient of 0.469 is statistically significantly different from 0 because the p-value is less than 0.05. Now also we get the 95% confidence interval for the correlation as well, and so you see that range here of 0.339 to 0.581, and this is kind of the typical notation you'd use, 95% space CI for confidence interval, and within the brackets, if you're putting this in a report or something like that, the lower and the upper limits of that confidence interval. And just remember that the correlation coefficient itself of 0.469 falls in the middle of this range here, and that is what is sometimes called your point estimate. Okay, so let's interpret this now. All right, so the first thing that we need to talk about is the p-value, because if the correlation coefficient, if we can't treat it as statistically significantly different than 0, then we don't really interpret it. We stop there. And in this context, we just conclude that there's no evidence of criterion-related validity. And more broadly, we would say that the correlation, we can't treat it as being meaningfully different or statistically different from 0. Now, our conventional cutoff is a two-tailed alpha level of 0.05. So in other words, if our p-value that we observed is less than 0.05, so that's important, less than 0.05, then we conclude that the correlation associated with that p-value is statistically significantly different from 0. In other words, it's a significant correlation from a statistical significance perspective, okay? Which is the case here. Now, if this p-value had been, let's say, if it had been exactly 0.05, well, in that case, the p-value is not less than 0.05. It's actually equal to 0.05 and or potentially greater than 0.05. We would have concluded that this is not statistically significant, okay? All right, so we have concluded statistically significant in this case, which means we can proceed forward with interpreting the direction or the sign of the correlation and its magnitude or its size, okay? And so the first thing we can do is when we're talking about its magnitude or size, this is actually a correlation, this 0.469. We could probably, by most conventional standards, call this a medium or a medium-large correlation. In other words, it has medium or medium-large practical significance. So this is interpreting the correlation, because it's statistically significant, as an effect size. Okay, so how did I come with this medium or medium-large practical significance? Well, I'm really just kind of borrowing from some rules of thumb and some thresholds that Cohen came out with in the, I believe it was the early 90s. These weren't meant to be set rules, and really our interpretation from a practical significance standpoint of a correlation should be context dependent and specific. But it's nice when you're practicing and you're learning to have some kind of thresholds, even if they're somewhat arbitrary or not context specific. And so for our purposes, we'll say that the absolute value of a correlation that is 0.10 or greater is small. Once it hits 0.30 absolute value, let's say that it's medium. And once it hits 0.50 absolute value, let's say that it's large, okay? And so anything less than 0.10, we would say it's negligible. Even if it is statistically significant, it's not really a meaningful size correlation from a practical standpoint, okay? And so our correlation coefficient is 0.469 or about 0.47. So it's almost to the threshold for large, but not quite. So let's call it either medium or medium large, as I do up here. So you can take some liberties with those descriptions in case when you have some correlation coefficient values that are on that threshold of or are nearing or approaching one of the thresholds. Now note, these are absolute values here. So even if this correlation was a negative 0.469, we would still say that it's a medium or medium large practical significance or effect size. Okay, so how do we interpret, though, this correlation meaningfully, given that this is a variable is a conscientiousness test score variable, and this criterion variable is a job performance evaluation variable? Well, we can interpret it as follows. And you would only proceed with this interpretation just like we only proceeded with the interpretation explanation of the practical significance when we have found evidence of statistical significance first. Okay, and so the way that we can interpret this correlation of 0.469 that is statistically significant and has a medium or medium large practical significance, we would say perhaps that scores on the conscientiousness test are positively associated with job performance scores to a statistically significant extent. And we might even add in, or often we will, imagine this is part of a write-up here, this note, we might add some parentheses, and within the parentheses actually just include this more technical information here. And sometimes it's helpful too to add a statement that further explains. So you might say something, in other words, to a moderate extent. And the reason I'm saying moderate extent is because we found that medium-sized practical significance. We could say those who scored higher on the conscientiousness test tended to receive higher job performance evaluation scores. Okay, and so this is another way you could explain this that might be to different audiences that you might talk to. This might be more interpretable. You might be able to interpret it more easily. So I typically would suggest starting with a more technical statement like this, where you state in clear language whether if it's a statistically significant correlation, the directions, whether it's positive or negative. And then you might also add in some language in that statement about the size of the effect if it's statistically significant, so the practical significance, and then make sure you include some technical information. But I like to follow it up with another statement, whether I'm saying this out loud or I'm writing this into a report, in which I also explain it in a different way that might be easier for other people who maybe aren't familiar with correlation coefficients and statistics more generally to understand and to act upon and to make sense of, really. Okay? So that's you don't have to use this exact language, but I think it's useful to come up with some kind of template that you can kind of use and practice with that template to get comfortable with the language here. Now, one thing that I kind of glossed over here that I'd like to take a little bit of time at the end is the interpretation of the 95% confidence interval. Okay, So this 95% confidence interval, and here it is, 95% confidence interval. Again, lower limit is 0.339, so that's medium size correlation. Upper limit of the correlation, 0.581, so that actually gets into the large arena here. So it actually is above 0.50. The way that you could really describe this, a 95% confidence interval, is that it's likely that the range from 0.339 to 0.581 for the correlation coefficient contains the true population correlation. Okay, so somewhere in there, it's likely that that's where the true population correlation lives or exists, is between 0.339 and 0.581. And again, our point estimate of 0.469 lives somewhere in the middle. And so this gives us an idea of kind of the potential spread of, well, really, where might that true population correlation be? What might that value be? Well, it could be anywhere from like a medium-sized value to maybe somewhere that exceeds our threshold for what would be considered a large correlation or a large effect. Okay, and so I just want to type here at the end that our correlation, so 0.469, this is our correlation, is our validity coefficient in this context. Okay, so just to remind us of that language, this is our validity coefficient, and we could say here that this is a significant or statistically significant validity coefficient. So practically speaking, given that this is an employee selection tool validation data that we're working with here, we could say this is actually pretty good here. We've got a medium to large size effect here, statistically significant correlation between conscientiousness test scores and job evaluation scores, where job evaluation scores are our criterion scores. And so this is pretty good. This shows evidence of criterion-related validity. Specifically, the conscientiousness test shows evidence of criterion-related validity. So I'll just make a note here. So the conscientiousness test shows evidence of criterion-related validity, and that is because this correlation here, the associated p-value, indicated that it was statistically significant. Okay. All right, so this wraps up this tutorial on how to estimate criterion-related validity using a correlation coefficient. And this is a correlation coefficient is an effect size. It's a standardized metric. We can compare correlations across different validation designs and so forth to see which ones are bigger, which ones are smaller, and so forth. And so in this tutorial, we specifically learned how to estimate a Pearson product moment correlation.